All right, 7-7, the photoelectric effect, and PES, photoelectron spectroscopy. And for the worksheet, I actually want you to do all the worksheet this time, and you'll see why. This is the topic of photoelectric effect has been for a long time in AP, but photoelectric spectroscopy has been something that has been on the AP for maybe about 5 years or so. I guess I'm going to guess that's about right. That they've really been concentrating on it, and it's a neat thing, and it's another way to apply what you know about electron configuration. So here we go. In your notes, it's session 7-7. Let me see. Oh no, did I miss? Did I put my own packet? Oh boy. Here it is. About to go nuts with this. Okay. Where am I? Okay. Electron configuration. Is this it? I gotta staple these things together. So it looks like that. 7-7. Photoelectric effect. Now I told you there were some puzzles. One was the bright line spectrum, early 1900s. Why in the world does every element give a different pattern of lights, a little line lights, when you look at them through a prism or through a diffraction grating? What was the reason for that? Another one was the photoelectric effect, and one was the black body radiation. And you know, I didn't really talk about black body very much. I just gave you a rough idea. I'm not going to go into it. I will say to look in your book and read the section about it, what they mentioned. But just know that a chemical or a substance or a metal that is a material that is considered a black body is one that absorbs all wavelengths of light, and it doesn't reflect any light. Like I told you, like my shirt is absorbing all colors of light, but it's reflecting this light blue wavelength of light. So photons, white light is hitting me, but only the light blue photons are coming off of this, okay? But all the others are being absorbed. Well, if every color is absorbed of light, nothing's reflected, so it appears to be black. That's called a black body object. Well, what happens though is that when you heat the object, oh, by the way, a black body object would also be given off infrared. You wouldn't actually be able to see. There would be some wavelengths in visible light we can't see, so they are being given off, but it just looks black. Well, anyway, for black body again, I know it's most boring for me to just talk about it and not show you an example, but I'll just mention that as you heat that object up, it starts to give off colored light, and you know, people were expecting, well, all right, first you see red light given off, then orange and kind of yellow, but then it skips. There's no, it skips all the way on, and it skips through the spectrum because of quantum. So anyway, that was one, and there's not a whole lot more mentioned on the AP about that. But now for photoelectric effect, there is a lot. This is what Albert Einstein won the Nobel Prize for. A lot of people don't know that. They all think, well, equals MC squared, and I'm sure there's a relation somewhere in there to that, but that wasn't why he won it. He won it because he answered a neat question that I'm going to show you right here, and you'll see how it's related to how it relates to quantum and what we talked about before. Okay, so here we go. It says in 1921, Einstein received the Nobel Prize in Physics for explaining the photoelectric effect. The photoelectric effect is this, and this was observed like early 1900s for a long time, that when light is shined on metals, electrons are ejected from the metal. And there was some puzzles about how fast the electrons that come off are moving. And it said, well, anyway, I'll just show this to you. How fast electrons are moving once they are liberated or taken from the metal. The speed of electrons does not depend on the intensity or the brightness of the light. That would be like if you see a wave, the brightness of a light would be also the amplitude. It only depends on the wavelength of the light. So here we go. I'm going to draw a metal. I'll just show you here. Let's just say that white. Well, we'll just use white light. Let's just say that light strikes this metal. Now, really, it's better to think of like a laser light, or here's the best example in the world is a remote control. When you hit a remote control. But when certain photons of light hit the metal, electrons are ejected. Okay? So here's kind of what they were finding out, and I'll just show you. Let's just say that let me see. I'm gonna try to use some colors here of light and show you like I did before. The brightness of the light does not affect what causes electrons to be ejected. So every metal, I don't know what these all, which they use. I think it's called, on the next paper, it's called the work function. Yeah, if you look down the bottom part below that, the work function, don't even worry about calculating this. We're not going to calculate anything you see on this actually. The work function is the energy required to remove an electron from the surface of a solid element. So work function would be the energy required to remove an electron. So here's the deal. So let's just think about Roy G. Biv. Can you remember where is the high energy and where's the low energy side? The highest energy light would be here. High energy, photon energy. High E photon for violet and then ultraviolet. And then low, going in this direction, it'll be low energy of photon. That's important to know. So let's just take this metal, and we'll call this metal X. I don't know whether it would be lithium metal or potassium metal or sodium metal. They all have different work functions. But let's just say that we shine red light onto this metal. Nothing happens, okay? Red. Say that we shine on metal X orange light. Nothing happens, okay? So red, orange, yellow, green. But now we'll let it be green. So we shine green light on it. And guess what happens? Electrons are emitted from it. Now, when you have a remote control, when you're pushing the remote control, you're actually sending a radio signal. Now, you can think of it, you're sending light. You know, you have to hit a sensor. You're sending light, probably infrared light for those things. I don't think you're certainly not going to be shooting ultraviolet light around in your home. It's infrared, but you're shooting that. We can't see it. It's invisible, but that light is striking a particular metal, and that metal, when you hit it with infrared light, will release electrons. So you push the remote control, whatever the electronics are. I don't know exactly, but I can tell you this: if you can cause an electron to jump out, and it can start a electrical current and turn on the object, like click, like a little shock, it turns it on. Then click again, it turns it off, or changes the channel, or however they got that wired in there. So that little metal is sensitive to infrared, whatever the metal they use inside it. Okay, so anyway, back to this. So green light, and now we're causing some electrons to jump off. Let's just say we cause, like, I don't know, let's just make 2 electrons jump off of that metal X when I shine green light. Now, interestingly, if I shine other colors of light, well, we'll get to that later. Okay, well, I better wait on that for now. So now, here was the puzzle. So they knew about this. So we think it's real cool, the technology, remote control. Now, even though we didn't have the technology that widespread back in the early 1900s, the scientists had the knowledge. They knew, hey, I can cause electrons by shooting a certain color of light at this, or infrared. I can cause electrons to jump off the metal. All right, and every metal has its own different frequencies that it can respond to. So if I shine green light, let's just say I get 2 electrons. Now, what if I make it a really, really bright light, a lot of green light? Well, they were expecting, since just like we would expect in a non-quantum world, well, if I add a little bit of energy, well, then I get the electrons leave at, I don't know, I'll make some number up, it won't be true. This is say they leave at 100 meters per second. Pretty fast, I guess, still. But if I put a lot really bright light, well, they're going to go like at, 200, more. I'm going to even give more energy. Well, it turned out that wasn't the case. What happened was, when you shine the light, let's say a small bit of green, a low beam green light, let's just say you get 2 electrons come off at 100, okay, at 100. Well, if you shine a little really bright light of green photons, and that was the answer to the puzzle, actually, photon theory, more. Now you just get a lot more electrons jump off, but they're all going the same speed. Okay, well, how can they be going? What scientists didn't understand was when certain lights are shined on metals, some would be going faster. And why is that? And Einstein said it's because of photon theory, the idea that white light is made up of all these other color photons. If you change the color of the light, you affect the speed. So if green light causes the electrons on here to move off at 100, well, actually, let me just leave it there. Let's just leave the green light back there. Let's say we take the same metal X, and maybe you'll get the idea. Now let's shine, well, okay, let's shine some orange light. So if orange light comes on there, now let's just say you do enough orange, so you also get 2 electrons moving off. 2 electrons are ejected from the metal. Okay, let's just go back to 2. We'll make it simple. So green light, 2 electrons at 100. Orange light, oh, I told you nothing would happen. Okay, yeah, nothing happens with that metal, with orange light. Let's just say that. But now let's say, well, okay, what if I put blue light photons on it? Now, we also get 2 electrons, but now they're going at, I would say, 175 meters per second. They're going faster. Okay, so the speed of the electrons depends on the frequency, or depends on the color of the light, which is the frequency. A higher frequency. So I know there's a minimal frequency that where you cannot eject. Like I said, metals have what's called the work function. So I just made up this metal to say, let's just pretend that metal, whatever metal this is, X, will not respond to anything before green. But now with green and higher energies, it will. Now I don't know, to be honest, if there's like, you know, could it be that there are some metals that like they'll only respond to green and they won't respond to blue? I don't think that's the case, but anyway, I've not seen that come up. All right, so anyway, that was basically the answer to Einstein's answer was it's because of the colors of the light that they're depending on the frequency of the photons that are hitting it, and the speed of the electrons being emitted depends on the photons the photons that are hitting it, the color of the photons, the frequency, high frequency. You know, high energy, high frequency is over here. And by the way, high frequency means low or short wavelength. Oh, I'm sorry. Yeah, short wavelength. Low energy of a photon means low frequency and long wavelength. And remember, the symbol for wavelength is lambda. It's good to kind of know that little chart, as I told you. That's why I said to know kind of like the electromagnetic spectrum and know that visible light comes into Roy G. Biv. All right, so I'm trying to think of how this would work. So anyway, that's good enough for right now to know that photoelectric effect, that's all it is. That it's not anything longer or crazier than that. But you see that the word quantized, I mean, it's interesting that energy particles or photons seem to have, I mean, the amounts of energy seem to be in little pellets. Like a red energy photon is low energy, and a purple energy is really high, or a green would be like in between them. So that's kind of the neat thing, and it's good to know how they compare to each other. All right, now there's a calculation about, well, let me see what it says here. Oh, I do want to, well, in experiment, electrons are ejected at 1 × 10⁷ meter per second from a metal plate. Example, when yellow light is shined on it. What will happen if the yellow light is dimmed? Okay, if it's dimmed, then less electrons. This is on the paper right here. If you dim the light, less electrons will be ejected. If you dim the yellow light, if you make a brighter light, more electrons, but they will all have the same speed. B, what will happen if red light is used instead? Okay, if red light were used, giving no other information, then you'd expect that they're going to go slower. They don't talk about whether it's dim or not, but the electrons will all go at a slower speed when they're ejected. Now, as I told you, there might be some metals that won't even eject at red, but so that could also be the case. And then letter C, what will happen if ultraviolet light is used? Ultraviolet light, they're going to go a lot faster because UV light will be this way on the spectrum. What if gamma radiation were on it? Well, then yeah, they're going to go off there really quickly. All right. Okay. So that works out pretty good right there. All right. So let me now show you. Oh, my children are having some problems with their Zoom, I guess, or something, or upset. Okay. So what I'm going to show you, one more thing. It's called Photoelectron Spectroscopy. All right. Now, I like this. It's a fun thing that you're going to see coming up. And it's a worksheet I put in here. I have not made an outline for this yet. And one day I'm going to need to do it. Like I said, it's been 4 or 5 years, probably 5 years. This might be the 5th year or whatever. But I've always just taught it this way, and it kind of works out. So this is an interesting thing. Now, what I'm going to show you, these are going to be some graphs. And let me start off by drawing. Let me draw out a graph here. All right. Now, on one side, I'm going to have relative number of electrons. So this is going to be a graph of what I was just talking about. Then down here, I'm going to put the energy. Now, a lot of times they use it in, I've seen megajoules. Yeah, megajoules per mole. Megajoules per mole. Now, I want to show you something they could do instead, though. And they have done this before, too. The energy could also be in kilojoules per mole, or it could be in joules per photon. Does that ring a bell to you? I showed you this in 2 different lessons. Kilojoule per mole, joule per mole, megajoules per mole. Okay, or joule per photon. So yes, if I were to use this equation and calculate the energy of the photon, of like this energy, this number, I'll pick up some number 1.5, well, it won't be 1.5. Yeah, well, actually 1.5 times 10 to the 15th joules per photon. If the energy of this little red photon, well, I'll just make it up for it, whatever, is 1.5 10 to the 15 joules for every photon, you should know how to turn that into kilojoules per mole or into megajoules per mole. You should know that. Okay. All right. I'll just add that to the side. I'm not going to be doing any math right here. Now, so I'm going to show you a graph. I'm going to try to make up one different than the ones that are right on your paper. So I'm going to put a little peak of a graph here. Maybe I'll go a little bit higher. Yeah, maybe up to there. I'll kind of make it a little bit easier. One there. Then I'm going to put one right here. Another peak. Then I'm going to put one here. And, okay, let me go like that. All right. So what in the world does this represent? Now, and there'll be numbers down here. Oh, and the numbers are often written in reverse. So I'll put, and they will be on the AP. They've told us that, and they're not going to change it. So let's just say that this is 500. I'm just going to make up 500, and this over here will be like, I don't know, 0 could be over here somewhere or whatever. We'll put maybe 100, 200, 300, 400. I'll just put numbers like that, somewhere around there. Okay, so what in the world does this mean? 500 megajoules, 400, 300, 200, 100. Okay, and you see these little peaks. Well, what's going on is, the idea is you're adding energy, you're adding energy to a metal, this much energy, and then electrons are being emitted off because of that. They're being ejected from the metal. Now, this could even happen with metals. I believe I've seen it could even happen in the gaseous state. That would be like ionization energy. Be very close to the same thing. And we haven't talked about that yet in this video. But what you're doing, you're removing the electron from the atom completely. But here's what I want you to see what's interesting about this. Relative number of electrons on this side of the graph, it actually can also be the intensity. Remember intensity, or how about brightness? Brightness, intensity, relative number of electrons. Remember we said the brighter the light, the more the electrons that you get, okay? So what you do is you shine a bright light of this energy. 400 would, well, supposedly 400 would tell you the color of the light, whether it's invisible or whatever. And then the brightness would tell you, how the intensity would tell you how bright it is, and that would give you how many electrons. So you shine it until that light is bright as you can and see how many electrons will leave. And look, 2 electrons can leave. 1, 2 for this peak. Well, then when this light is shined on it, 2 electrons leave. When this light is shined on it, it looks like 5 electrons can leave. What in the world could this represent? Guess what? 1s2, 2s2, 2p5. Really? So what the graph is actually giving you what the element can be. Now here's the interesting thing. I will go over here and let's just see. So what element is 1s2, 2s2, 2p5? It's going to be fluorine. You see on the chart right there, 1s2, 2s2, 2p5. All right. So that would be fluorine. This would be a photoelectron spectrogram, I guess you call it, spectrograph, yeah, of fluorine. Just elemental, it'll be the F. We won't put F2, we won't mix with that. So, all right. Now, a couple of things you need to know. Why is it 1s 400 to remove them, but to remove the 2p's it's only 100? Well, it has to do with where the electrons are in the atom. Now we can kind of think of this model. Though it's not true, let's think about this for a second and see. Electrons that are at 1s, let's just put them right here for a second. 2 there. Then you have 2 at 2s, we'll just say. 1s, 2s. Then 2p will be a little bit higher than that. 1, 2, 3, 4, 5. I'll just put some numbers around. Now, I don't want you to... If you ever did something like this and explaining it, that will be okay. But yeah, but we don't actually officially draw Bohr models. But what I wanted to show you is this. Here's your nucleus. So who's going to be held the most strongly to the nucleus? It's going to be the ones that are close to the nucleus. Now, there's actually Coulomb's law tells us K, Q1, Q2 over R squared. You'll see this equation that tells you the energy of attraction between positive and negative is equal to the charge. Like say an electron is -1 charge, the nucleus is positive, whatever the number is positive, whatever, it doesn't matter. And the radius is how far you are. All you need to really think about, positive, I'll just put positive 10. Well, actually for fluorine, what is it? Positive 9, right? Yeah. Okay. So anyway, all of these electrons, if you do each single electron now, were to calculate the energy of attraction right here with the nucleus, they all will have positive 9 for the nucleus, the same nucleus, but now, and they're all -1. The only thing different is how far are they, the radius. And notice, maybe that picture makes it a little bit harder to see, but an electron that is closer to the nucleus has a small radius. If that number is small, the energy is greater. If that number is really large, then the energy will be smaller. See, as that number increases, the overall value for the attraction goes down. If that's a real small number, the energy goes up. Well, anyway, what it's saying is, it's just like your weight. Think about gravity, because gravity is a lot like this, and I'll talk about this in a later lesson. If I'm standing right on the surface of the Earth and I weigh myself, I'll see the weight and like, oh boy, that's my weight. But hey, take me up to the space station, okay? So then they're gonna put you on the whatever space X or whatever, go to the space station if they ever do that. And now you weigh yourself and you're like, wow, I weigh a lot less. This is good. Hey, I'm getting in shape. So anyway, when you go all the way up to away from farther from the Earth, you weigh less. Okay, so less energy up here, less energy, more and more and more as you get closer. All right. So the electrons that are really close to the nucleus have. So here's the bottom line, quick answer. Why are these the 1s electrons and 2s? Why are 1s at 400 and 2s? Because 1s electrons are closer to the nucleus, therefore they have a greater attraction. The nuclear charge, a greater attraction. It's harder for them to be ejected. They need more energy than the 2s electrons do. Okay, that's the bottom answer. But I just gave you a long explanation that you wouldn't need. But we're going to be getting into some things like that pretty soon about some discussion. So anyway, 1s2, 2s2, 2p5. All right, now let me throw in some more stuff here. So let's just say, let me just check for a second. I'm trying to think of some examples, and I don't want to give exactly what your answers are going to be of this. So let me just pick out. Okay, let me pick neon for a minute. Looks like I don't ask you about neon on the paper. Let's get carbon and boron. Let me see. This, nitrogen. Okay, good. All right, so let's talk about neon. What would neon look like? If I had to draw with a green, I'm going to draw neon in green. So this is fluorine. So the white is fluorine. Now I want to put a green, and they could ask you to do this too. Draw in neon, okay? Neon, not nitrogen, neon. Okay, neon, you say, well, it's 1s2, 2s2, 2p6. All right, you're not going to is it going to go over the same ones? No, it won't. Because neon, think about it, has a greater nuclear charge than does fluorine. So since the nuclear charge is greater, the 1s electrons in neon, should they be, if neon has a greater nuclear attraction, nuclear charge, positive 10, should it be harder or easier to remove the 1s electrons in neon? It should be harder. It should take more energy. So I'll just go to 450. So neon might look like that. That would be 1s. Oh, it should be up and down with a little peak like that. That should be 1s to there for neon. So it's still 2 electrons. Should be right on that line. Then 2s2. We'll just put it right somewhere in between there for neon. And then 2p6, the same thing, should also go, but it's going to go higher. It's going to go all the way up to 6 electrons, 2p6. So 1s2, 2s2, 2p6. Right. Now, if I put an element like, okay, just put in only maybe who? Should I just do beryllium? Yeah, maybe I'll just do beryllium. Beryllium is, I'll use like, let me see. I'll just use an orange for that. Oh well. Let's just say that I put in beryllium. Now beryllium's nucleus, compared to neon and fluorine, I'm not going to be able to fit all this on here, but, well, I can. Beryllium is going to have positive 4 nucleus, so it's a lot smaller. It's a lot less, lot lower charge. So it should be, if it's down to positive 4, real small nuclear charge, it should be easy to take away the 1s and the 2s electrons with that. So for boron, it would look like that. So I'm going to go orange up to there, then orange up to there, and then there is no 2p for boron. So it's 1s2, 2s2, and that's it. Beryllium, I said boron, I'm sorry, beryllium. Boron does have a p. So 1s2, 2s, 2s2. Okay, all right, so you kind of get the idea. I think I've just about told you everything you need to see about that. When you see one, like if you look on the worksheet, when you get to the right side of the paper, it's going to ask you like what element is this, and I'm just telling you, starting from the high number here to start going 1s. Each peak that you see, we'll talk about one element. Okay, so let me just draw. Let me make up one again. I'll just make up something else here. So let's just say that we have a peak that looks like a. Why don't I use? I don't know. I better use that color. I can use another color. Yellow might show up good. Okay. So if I did an element like this, let's just say if I go like this, and now I go like that. What could that be? Well, that would be 1s2, 2s1. Okay. So now we didn't go as high in the s's as you see there. Okay. So that's another little thing you might see. And then, of course, 1s2, well, I'm sorry, 1s2, 2s2, 2p6, 3s2, 3p4, okay, or whatever it might be, as we're showing you. So anyway, I don't think you have to worry much about the D's and stuff. 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4, 3p4. Okay, so anyway, you can just go straight along this way. Okay, I'm not going to, that's all I'm going to say about it. So answer the questions that are on the paper, and then at the very end, it's going to ask you what these two elements are, element for letter A and letter B. And I'm going to try and find some other, I saw some good resources, some other practice on this that I'll show you. Oh, I know one little thing I was going to tell you. And I'll tell you what, you kind of have to go back. I'm not going to go over the whole thing now, but I want to say this is really important. I just want to show you. Like, look at the graph that I have here. Let's just say that this is let's just say this is joule per photon down here. All right, so joules per photon. Or I'll make that up. Or no, well, no, I got a better idea. Let's say kilojoule per mole. All right, let's just say this is kilojoules per mole. And let's say, which one is it? It's kind of close on it. That one is. It looks like the 2s electrons are 400 kilojoules per mole. If I were to say, what's the wavelength of that light? What is the wavelength? Calculate the wavelength of that light. Well, here's what you do. You have to go back to the lesson that came before this, the one that we did on Bohr model, okay? And you go, I don't think I'm going to do it. Let's just see. I'll just say it real quick. Kilojoule per mole. First, I'm going to change that to, I got to get to joule per photon, okay? I got to go to joule per photon. So kilojoules to joules. 1 kilojoule is 1,000 joules. And then instead of having mole on the bottom, I want to have photon. Mole will go on the top. 1 mole is 6.022, 10 to the 23rd. You'll get your answer in joule per photon. I'll tell you, you're going to get this answer, and I guess I'll get it quick, whenever. 400 times 1,000 divided by 6.022, 10 to the 3rd. It looks like 6.64, 10 to the negative 19. 6.64, 10 to the negative 19. So let's just say you pick a point on here, and you have kilojoule per mole, so you change it to joule per photon. Now, I can use this equation and plug in 6.64, 10 to the negative 19, and I can count and put in 6.626, 10 to the negative 34. That's Planck's constant. And find the frequency. Then I can use lambda nu equals c to find the wavelength. Okay? So you can actually find what the wavelength and the color of light, if it's visible. They can give you a list of colors. This is my prediction that they can do this sometime on the AP. But there's also one more thing. I'll just show you real quick. This equation. This equation is not really given. It's not given on the AP sheet, but if you ever wanted to use it, you could. It combines E times EH lambda and then lambda nu C. I know we call it EHV and lambda VC. It's not V, it's a nu, but well. But anyway, if you combine them together, you get this equation. And this would let you go quicker. Like if I put in the energy right there, and I put in Planck and speed of light, I can calculate in one quicker calculation. Instead of having to use, two equations, I could use one equation. Just wanted to show you that a little bit. All right, I'll see you guys.